Hi, I'm Manoj Kumar, founder of Futuretron Labs, which is a makerspace as well as a startup in the e-mobility solutions, where we work on different e-mobility solutions as well as different chemistries of lithium-ion batteries and battery packs. Recently, a client of ours came to us with about 106 numbers of lithium ferrous phosphate battery packs. Can we salvage it and make it into a different battery pack? These are the battery packs he gave us. So these battery packs are of 24 volt and 24 Ah. And then when we check the voltage of these battery packs, the output voltage was showing somewhere around 2 volt, 5 volt, 6 volt, and then some of them even showed about 18 volt also. So initially we thought like we'll charge them directly and then separate the cells and make it into different solutions. As you all know, like lithium ferrous phosphate cells come with a nominal voltage of 3.2 volt and a completely charged voltage of 3.6 volt. But a 24 volt, 24Ah battery pack giving 2 volt, 3 volt is something that needs to be looked into, right? So what we did, let's go ahead and see what we can do out of these batteries. Test the voltages of these batteries now and open the battery pack and see what we can do. As you can see, we have separated the batteries from the battery bank. Now let's test the voltages of each individual cells and then separate them or classify them based on the voltages that they have. Let's go ahead and do it. So as you saw, we have segregated the cells into different voltage in the battery pack. Now we cannot use these cells to make it into a different battery pack. And why? Just with the charges, with the voltage itself. Voltage is unreliable for checking the state of charge. So what we are going to do? So these battery packs came with these bus bars. So I'm going to use these bus bars and connect them parallelly first. So what happens if I use these cells directly to make a battery bank is like so either of the one of the cells will be high voltage and other cell will be low voltage, and because of that reason the BMS will cut off the output due to the high voltage cutoff or low voltage cutoff. Commercial BMSs comes with the balance function. Takes a very long time to balance these cells to maintain the state of charge. Okay, and the other way to balance these cells is connect them parallelly and leave it for a long time. So what happens with these thing is the cells have the tendency to move from higher state of charge to lower state of charge over a period of time, like a weeks or even months. This will all the state of charge of all the cells will come to the equal, and then all those things will be balanced. And the other way to do this one is by top balancing. Top balancing in the sense like connecting all the cells in parallel and then charging them negative to negative, connecting a SMPS base charger with a controlled voltage and a controlled current to charge it. So once the entire cell pack is parallelly connected and charged, the load that goes into the battery or the cell pack will reduce it to zero. Once the current reduces to zero, it means that all of them have equal charge. Let's go ahead and do the things that I said now. So all these individual battery pack will connect it parallelly from negative to negative, positive to positive. Right now I've connected all the 4 cell packs which are connected parallelly to SMPS base charger, where I have kept it for 3.52. The voltage will increase to 3.52 once some charge goes there, and then the maximum discharge in this case is 16.4 amps that this SMPS charger can give. It is giving that much, and this might take like a day or two to completely charge, and then the 1 amp becomes zero. So now the parallelly connected batteries are charged to 3.41 and state of charge is constant without the batteries. Hi, welcome. 2 days before, we had removed all the cells from the battery pack and then we had put it for charging. Right now it's completely charged, and in meanwhile we have made a 32650 cell holders. I mean, this you get it into individual pieces and then you plug it like a Lego and this becomes like this. So right now we have made 8x7 matrix where we are going to make 12 volt and 84Ah battery points. Let's go ahead and see like how we are going to arrange these cells. Since we have made this configuration of 12 volt 84Ah battery pack using old salvaged LFP batteries, we have to connect it in series and parallel to achieve a 12 volt 84Ah, and this will be used for higher amp applications. So what happens in higher amp applications is, as the load draws more current, there will be a lot of heat transfer that happens between the connections. So what we thought was, let's use these 0.75 mm copper plates to connect these series parallel connections. And for the same, we have made a jig of connections. 7 holes that goes like this, and then 4 holes for a series connection like this. Since we have a jig, we are going to use this copper plate. We are going to cut it using angle grinder, and then we are going to drill holes for the holes that has to go in. Let's go ahead and see how this comes out. As you can see, the voltages across these two terminals, positive and negative, of this handmade LFP batteries 13.04. So last time we did the battery pack using copper plates. It's a tedious job, but the cells that we had nut and screw arrangement. So the other way to do it is using nickel strips. So that this is Manju, he's a colleague of mine. He's going to show you how to do it using nickel strip, as well as connecting the 12 volt BMS to it. And then finally we are going to assemble completely and put it to use in an inverter. Let's go ahead and see it.
So we have a 12 volt 84Ah LFP battery pack, which consists of a total number of 56 cells. Each cell is specification of 3.2 volt and 6 Ah. In order to make a 84Ah battery pack, we need 14 of these cells to be connected in parallel and 4 of these packs to be connected in series. So in order to make a 14B pack, we need to connect all of these 14 cells in parallel, which are connected using this nickel strip. In order to make a 12 volt battery pack, we need 4 of these individual blocks to be connected in series. So I'll go through the process of connecting them in parallel and as well as in series. So to make the parallel connections, all these negative terminal are connected using the nickel strips. So thereby all these individual connections are common. The positive is also connected in parallel. As you can see, everything is interconnected to each other. So all of these 4 blocks are connected in series. So this is the negative of the first cell, positive of the first cell, which is connected to the negative of the second cell. Positive of the second cell is connected to the negative of the third cell. Positive of the third cell is connected to the negative of the fourth cell, and a positive terminal is connected using the nickel strip, and all are interconnected, as you can see. So we can measure 12 volt across the positive and the negative terminal. this is the BMS that we'll be using for our today's battery pack build. So it has a continuous discharge current of 60 amps and a charging current of 30 amps. B minus is connected to the battery's negative terminal, and this is the output wire for the negative terminal. On the left we have these balance leads which need to be connected to the respective cells positive and negative terminals. Let's go and see how we connect this BMS to the battery pack. Okay. So here we have connected the BMS now. As you can see, the B minus is connected to the battery's negative terminal, and the balance leads are like the black wire is connected to the negative terminal. The next red is connected to the positive of the first cell. The next red is connected to the positive of the second cell. The third red is connected to the positive of the third cell, and the final red wire is connected to the positive of the final cell. So here this positive black wire is nothing but the common wire for both charging as well as discharging, and this black wire is for the common negative for both charging and discharging. So let's test the output voltage. So finally we get the output voltage correctly with respect to the cell's voltage. Now we'll go test this battery pack connecting to a load and see what its working and capabilities. So once the battery pack is completed and all the BMS connections are completed, we have connected it to a DC load that we have built here. So this is a DC load that we have built which is capable of discharging around 300 watts of power in terms of heat. The BMS is working properly. Let's now go and pack the battery. So the battery pack is ready now. So we have designed a special enclosure for this battery pack. So I'll show you the enclosure now. So this is the enclosure that we have designed for this particular battery pack. Let's now go and place the battery inside the compartment and see the total output. So now the battery pack is ready. Let's go and test this finally with the inverter and see what will be the output, and we'll see the final outcome. So now we have connected this 12-volt battery pack to the 850 watt VA. Let's see the connection of the battery. So we have connected the positive wire of the inverter to the positive of the battery, and negative wire of the inverter to the negative of the battery. And the AC in for the inverter is connected to a junction box. So this is the AC input voltage of 250 volt AC. And this is the battery voltage, which is 13.1 volt, and it is currently in charging state. The AC is connected to the inverter. Let's now connect the angle grinder to the output of the inverter and see the load capacity and